Good afternoon. My apology for not being able to attend this important event in person. My talk today is about our ongoing research towards building resilience through reconnaissance. I will focus on several approaches for artificial intelligence that we have been studying as they relate to structural health monitoring. I would like to thank California Department of Transportation and California Department of Conservation for their financial and technical support. Many researchers and students contributed to the work I am about to present, and I would like to thank them for that. After the introduction, the talk has two parts: vibration-based structure health monitoring and vision-based structure health monitoring. The research I am presenting takes place within the Pacific Earthquake Engineering Research Center, which is an alliance of university, government, professional, and industry. It has 11 core institutions and 9 educational affiliates. PEER combines resources of research universities in the western United States where earthquake hazard is large. Please make sure to subscribe to our news by joining through the shown website peer.berkeley.edu. Peer activities related to SHM are grouped into vision-based, text-based, and vibration-based. For the purposes of real-time and long-term monitoring, automated, accurate, and reliable decision-making, and reconnaissance of the built environment. Today, I will only focus on the vision-based and the vibration-based structural health monitoring. Speaking of reconnaissance, I would like to draw your attention to the Structural Extreme Events Reconnaissance Network. It covers seismic, wind, and coastal hazards. You can become a member through the website steer.network by filling a simple form. The network is built on an integrated framework to accelerate data to knowledge life cycle. This is done through coordinated reconnaissance following natural hazard events, where the goal is to make use of the field observations of the affected communities to directly inform research and development and simultaneously affecting the regulatory mechanisms. This is in lieu of the used cycle of field observation, informing research and development, then influencing the regulatory mechanisms, which takes longer time. Gathering field observation via reconnaissance is closely related to different forms of structural health monitoring that we are discussing today. BRACE2 is a Bridge Rapid Assessment Center for Extreme Events to develop a data and simulation framework for real-time rapid and near real-time comprehensive assessments of instrumented bridges in California by taking advantage of their sensors to evaluate their conditions following earthquakes. Sensors are typically accelerometers for vision-based SHM and cameras or drones for vision-based SHM. Upon processing, learning, and analyzing the multimodal data, where we couple physical twin with digital twin through sensor data, system identification, finite element simulation, we achieve rapid or detailed maintenance decisions. Forming Brace 2 is motivated by the fact that in the past 20 years, about $25 million were invested by Caltrans in the California Strong Motion Instrumentation Program for bridges. Brace 2 will demonstrate that such instrumentation can evaluate the bridge conditions and help the mission of the maintenance and post-earthquake investigation team. The map shows the stations of Caltrans CICM on bridges. Note that San Francisco Bay Area has the most number of instrumented bridges, about 30 bridges. Brace 2 started about 3 years ago with 5 bridges, as you see in the images, where Bridge 1, referred to as Hayward Bridge, is the main one to develop a complete digital twin and monitor it in real time. The other 4 bridges are used with their historical data, which means they are not monitored in real time data streaming. 3 of these bridges are in Northern California, while the other 2 are in Southern California. The bottom right is the Brace 2 platform interface, and in the coming slides I will talk in more details about this platform. The Hayward Bridge is shown in this slide, which has 32 channels of recording, 20 on the superstructure and 12 on the East Geotechnical Array. On a high level, Brace 2 platform consists of a decision-making core. It receives data from the 32 channels of accelerometers through California Geological Survey real-time data streaming to Brace 2 server for the case of Hayward Bridge. It also has several pre-developed structural components to determine the capacity of these components, which are used for real-time damage assessment. It also has global bridge models of multi-fidelity for near real-time comprehensive assessment. This slide shows the computational model of the Hayward Bridge, which is developed in OpenSeas and considers all the details of the model, including in-span hinges, abutment models, different constitutive models of columns, the bridge deck, and so on. Several models are listed here, which were explored during the development of the multi-fidelity models of the Hayward Bridge. For example, M1 is the simplest, M5 is the most sophisticated. They include different modeling assumptions for the connections between the column and the cap beam in this case. Brief results are shown in this slide related to the 3 fundamental modes of vibration in the transverse, longitudinal, and torsion modes in comparison between the OpenSeas model and the system identification results from the data, showing reasonable agreement with some room for improvement, for example, for the longitudinal mode, where improved models of the abutment and soil structure interaction are currently under development. Several system identification methods are implemented in the Brace 2 framework, including single input, single output, multi-input, multi-output methods, where recorded for the instrumented part of the bridge or simulated for the non-instrumented part of the bridge acceleration data are processed to estimate the vibration characteristics, The histogram shown on the top left shows all the recorded data sets from April 2021 to January 2023 that have been streamed in real time from the instrument on the bridge to the BRACE2 server. This slide is a comparison between the results of the system identification methods that were implemented in BRACE2 for the three fundamental modes of the Hayward Bridge for two earthquakes. An older one that took place in 2018, that's on the top left, and a newer one, the bottom right, that took place in 2021 after implementing the real-time data streaming for BRACE2. They are comparable to each other because these are small events and no change in the bridge that's expected from these two data sets. A unique feature of BRACE2 is to relate typical damage states in terms of drifts or strains to action decisions typically used by the structural maintenance and investigation team using the first responder bridge assessment guide. So here we relate these damage states with the shown description here to these ranges of operation, R1 where the bridge remain open, R2 and R3 the bridge either open or closed but inspection is called for, R4 is when the bridge is immediately closed. This translation is reflected here on the pushover curve that relate drift ratio to base shear for one of the bends of the Hayward Bridge, where the damage states are superposed on the pushover curve. Here we show two of them. One is generated using OpenSeas, the other is generated using Abacus for comparison. And you see the ranges of operation are superposed. This is useful in rapid assessment of the component conditions and accordingly making a decision about the bridge operation. Finally, the BRACE2 platform shown in this slide has the dashboard with a snapshot of the managed bridges. It has all events of these bridges in the inventory, which shows the numbers next to the items in the inventory 1 to 5 representing the considered bridges at this stage. The other ones that are not numbered are potential future extension of BRACE2 with other monitored bridges. Several evaluation metrics as shown at the bottom left here that shows the OpenSeas model of the Hayward Bridge, and at the bottom these metrics in terms of peak acceleration, strain damage state, and peak displacements. The second part of this talk is about vision-based SHM. This research has been carried on since 2017. We typically use different forms of deep convolutional neural networks to perform different tasks of classification, localization, and segmentation from images, as shown in the example on this slide for concrete cover spalling identification. In this work, we identified and presented different research demands that you see in the first column here, scientific challenges, main achievements, and application scenarios. In this part of the talk, I will only touch upon three achievements, namely the automatic detection datasets, or the so-called FENet and FENext. The second is the pre-trained structural image net model, or SIM, coupled with transfer learning. The third is the interpreting deep learning model, the so-called Sigma box. And finally, an application of concrete crack identification that is called CICM for bridges is discussed. The first step for vision-based SHM is to develop a database. The database we developed is called PHENet, which stands for Peer Hub ImageNet. It has 8 tasks for the scene level, the damage state, spalling condition, material type, collapse mode, component type, damage level, and damage type. These are arranged in a tree structure and documented in a peer report that's shown in this slide. It's publicly available, and the data set itself is open source. At this stage, PHENet has only about 40,000 multi-labeled images. This is not a large number. Therefore, we made use of transfer learning from a source domain, which is ImageNet, that's developed by researchers from Stanford and Princeton, to a target domain making use of the small dataset PHENet. This resolves the limited dataset size by training for the low level feature on the source domain and fine tuning for the high level features on the target domain. This approach of transfer learning for damage recognition allowed the determination of the best deep learning model for the different PHENet tasks, as shown in this slide. This can be used for benchmarking future models using the PHENet dataset. The table shows different best models using as a backbone ResNet and VGGNet with and without transfer learning and data augmentation. And the corresponding best test accuracy ranging from 93% for easy tasks, usually binary outcomes, to about 72% for harder tasks with more than 2 outcomes of each of these tasks, like the case of the damage type, for example, that could be flexure, shear, combined, or none. This is our original work documented in this paper that was published in 2018. The developed SIM, or a structured ImageNet model, was used for reconnaissance activities following several events. Here is an example for images, 5 images, where SIM predicted their labels for several tasks, showing excellent outcome when compared with the ground truth in terms of the probabilities of the different outcomes of each task. So you see, for example, for the damage state, the case of undamaged versus damaged for sample 1 lead to a decisive decision that this is a damaged state. Some cases, like the case of sample image number 4 for the component type, the algorithm is somewhat not very precise in deciding whether this is a component of a wall or a column. So it gives about 41% for a column, 55% for a wall. So it is indeed a wall, but because of the existence of boundary columns, it was somewhat confusing to the algorithm. PHENet was recently extended to the so-called PHENext by adding 2 more tasks related to damage localization and damage segmentation. And the paper that discussed PHENext came out actually early this month. In addition to the extending PHENet in PHENext by adding 2 more tasks, The vision-based SHM was reformulated in this recent paper into multi-attribute, multitask transformer framework where the images have multiple labels. This framework is called MAMT2, M-A-M-T, the number 2. The application of phi-next and MAMT2 is shown in this slide for task 9 for localization and task 10 for segmentation, where the results from MAMT2 are compared with the state-of-the-art mask region CNN. This is done for 10 images, as you see here. The top part is for localization, where you see, if you look carefully, you see the bounding boxes that the network determine, and the bottom show the mask that represent the damaged region, for example, concrete spalling or cracking, and the ground truth is right in the middle. So for both tasks, MAMT2 did a better job than mask region CNN qualitatively and quantitatively for both localization and segmentation. The last contribution I would like to share with you is related to the vision-based SHM and its interpretation using the Structural Image Guided Map Analysis Box, or for short, Sigma box. It's fully documented in this paper for the purpose of giving explainable artificial intelligence in the context of structural health monitoring, where we start with an image, as you see here, step 0, then proceed with forward propagation and backward propagation as usual in any training of a CNN. But we add a step 3 for generating and outputting saliency maps that are used for model evaluation. So this is referred to as the Structural Image Guided Map Analysis Box, or Sigma box. So in this way, we generate heat maps that identify the region of the image that influence the prediction of the network. So here is an example of 3 images identifying regions which trigger the classification for damaged or not damaged, as in the second column. The ground truth is the first column. Spalling or not in the third column. Component type, column or wall, in the fourth column, and finally the damage type, combined or shear type, in the last column. So these heat maps are very useful in explaining the reason for the network to predict what it predicts. Very important when you use artificial intelligence in an important application with major consequence like structural health monitoring. Here I show one application documented in the shown paper where we consider bridge structural health monitoring for crack detection. The framework is made of 4 steps referred to as convolutional active learning identification segmentation measurements, or in short CAL-ISM. In step 1, we start with a pre-trained benchmark model. Then we go to step 2 for crack recognition modeling, step 3 for crack segmentation modeling, step 4 for maximum crack width and orientation calculations. To be a little more specific, here I show a picture of a crack where we find the crack mask to get rid of the background, and then we extract the crack edges. Here it's shown for a small part of the crack on the pixel level by zooming in. Then we can use this information to determine the projection angle of the maximum width of the crack, and finally conduct width and angle calculations. In the coming slides, I compare the obtained maximum crack width D, that's shown here, with the actual crack width if it's known through the so-called recognition error. This framework was applied to several laboratory bridge piers which were tested for excessive level of loading that led to damage and cracking, concrete spalling, and so on. And results were very promising qualitatively and quantitatively, with maximum recognition error of about 13% for these identified 10 cracks that you see here, and you see the recognition error of a maximum of 13%. There are two values for cracks 8 and 9 of higher value than 13%. This is due to surface defects, not due to comparison with the actual crack width. So the surface defects led to erroneous determination of the actual crack width. And this part here of these 10 cracks correspond to these 10 cells of the grid to which the specimen was divided into. Finally, CAL-ICM framework was applied in the field for two bridges in Shanghai, China. You see the image here, different images for data collection and also crack width and orientation measurements for establishing the ground truth. The results were very promising, with about 12% recognition error for one bridge and less than 3% recognition error for the other bridge. And you see the mapped cracks here in these two sketches for the two bridges. Finally, we come to the concluding remarks. I can say that the objective of the BRACE 2 is post-earthquake real and near real-time damage and functionality assessment of bridges with physics-based and data-driven methods using sensor data and numerical simulations. This have been achieved. The advances and results in AI-enabled structure health monitoring show high potential of this approach in structure engineering applications, particularly with now the available open source FEENet with its 8 tasks and FEENext with its extended 10 tasks. With improved monitoring, cheaper sensors, data fusion, and machine learning, the maintenance and effective decision-making about conditions, replacement, retrofit of key elements of the built environment, whether it's bridges or buildings, can be reliably achieved. The future research is expected to continue and to take place for early stage warning using vision and vibration-based SHM. Finally, this line of research is expected to enhance the resilience of the built environment, where rapid actions are recommended to decision makers, for example, bridge operations and maintenance or emergency responders. With that, I thank you very much. And once again, I am very sorry I couldn't be there in person. I was looking forward to be in Dhaka and meet many friends there, but unfortunately, unexpected circumstances prevented me from being there. Hopefully, in the future, there will be other opportunities to join you in person. Thank you.